In continuation with the previous part, the next derivation is of theorem of parallel axis. It states that the moment of inertia IO of an object about any axis is the sum of the moment of inertia IC about an axis parallel to the given axis passing through the center of mass, and the product of the mass of the object and the square of the distance between the two axes, that is mh square. Okay, this is the statement for this theorem. You always require to write this statement. Now let's start with the derivation part. These are the two axes which are parallel to each other. This axis MOP is an axis passing through point O, and axis ACB is an axis passing through center of mass of the object, which both are parallel, and it is separated by a distance h from it, that is CO is equals to h. Okay, so this axis passing through MOP is the IO, and moment of inertia for this axis is IC. Consider a mass element dm located at point D. Perpendicular on OC from point D is dn. This dn. Okay, this is perpendicular. Now as I told you, IC and IO. Okay, so the this related to IC will be this DC, and for IO is DO. So here what is written? IC is equals to integration of DC square dm, and IO is equals to DO square dm. See again, IC DC and IO is DO. Okay, so now IO is equals to, we will consider this first. IO is equals to DO square dm. Why? Because in the statement part we have, first it is IO only, we have to prove the moment of inertia only. So IO is equals to integration of DO square dm. So DO square, if you see this DO square, it is a right angle triangle, so it will be DN square plus NO square. Okay, so DO square is equals to DN square plus NO square. And if you see NO is NC plus CO. Okay, so after that NO, NC plus CO. Now for this you are going to apply the formula for A plus B whole square, that is A square plus 2AB plus B square. Okay, now we already stated that CO is H, so we are going to substitute the value of CO as H. So H here and H here, and this part DN square plus NC square, again DN square plus NC square will give DC square. This is Pythagoras theorem. DN square plus NC square will give DC square. So here this 2 will give DC square, and here we have substituted this 2 value. Okay, so now we are going to separate the integration part. So DC square dm plus 2h is constant, NC dm plus h square is again constant, so therefore 1 dm. Okay, this dm will go everywhere, and this integration will also go everywhere. Now NC is the distance of point from center of mass, so the mass distribution is symmetric. So from the definition of center of mass, integration of NC dm will be 0, and integration of dm is m. So IO is equals to this DC square dm is IC, so it will IC plus 0 plus h square m. So IO is equals to IC plus mh square. This is the mathematical form of theorem of parallel axis. Next, theorem of perpendicular axis. It states that the moment of inertia Iz of a laminar object about an axis perpendicular to its plane is the sum of its moment of inertia about two mutually perpendicular axes x and y in its plane, such that all the three axes are mutually perpendicular and have a common point. So this is the diagram. Consider a rigid object which rotates, and all the three axes are mutually perpendicular. Axes x and y are in plane of the object, while z is perpendicular to it, and all are concurrent at point O. So if you consider mass element dm, it is located at point P. Pm is equals to y and Pn is equals to x. Okay, this is parallel to this is parallel to this, so it will be x and this will be y. If the moment of inertia of the body about x and y are ix and iy and iz respectively, the moment of inertia about its axis are ix is y square dm and iy is x square dm. For iz you will add this. Okay, and the respective perpendicular distance of point m from x by z are y x, x का y का x and z का root y square plus x square. Okay, so this again you separate this and you will get this for ix, this for iy. So this is the mathematical form of theorem of perpendicular axis. Next derivation is conservation of angular momentum. When no external torque acts on the body, the net angular momentum of rotating rigid body remains constant. This is known as law of conservation of angular momentum. We know that angular momentum is given by L vector is equals to R vector cross P vector. This is the formula for angular momentum, where R is the position vector from the axis of rotation, P is the linear momentum. Now we are going to differentiate this all with respect to t, with respect to time. So dl by dt is equals to d by dt r by r vector cross p vector. Now friends, see, this is cross sign, that means multiply. So for derivative you cannot take the derivative directly. This is product. So for derivative there is a product rule, d by dx uv. These two are separate terms and in multiplication, that is product. So for this it is a formula there. You're going to take u out and you're going to take derivative of dv by dx. Then plus v will remain out and you will take the derivative of u part. Okay, using this formula you're going to derive this. So u, this is u, this is v, so this will remain here. You're going to take the derivative of this dp by dt plus sign, you're going to remove this and then derivative of dr by dt. Okay, derivative of this p is f and p is equals to mv and dr by dt is v. Okay, that means when you differentiate the linear momentum you will get f, that is force, and when you differentiate the radius you will get the velocity. So you are going to substitute here r vector, this is f plus m, p is equals to mv and derivative of this is v vector. Okay, so m, the cross rule, v vector into v vector, just you have simplified this, because this thing you will get 0, so this whole term will get 0 and it will be r into f, which is nothing but torque. This is torque. So torque is equals to dl by dt. If torque is 0 then this will also be 0, that means L will remain constant. Hence angular momentum L is conserved in absence of external unbalanced torque. Thank you.